All right, section 15.2. We're going to talk about energy and how it's converted from one form to another. Can energy be converted from one form to another? Absolutely. Think about that. If you're sitting on top of a hill and not moving, you have a lot of potential energy. What would happen once somebody pushes you down the hill when you're sledding? You start moving really fast. So a lot of your potential energy is converted into kinetic energy. Think about when you jump out of a plane. Do you have much energy when you're standing on the plane? You have a lot of potential energy. What happens once you jump out of the plane? You start going really, really fast, and you've converted that potential into kinetic. So we're going to focus on what happens when you can convert potential into kinetic. So as I just mentioned, energy can be converted from one form to another, and the process is called energy conversion. Now, what are some examples? Well, there's a bunch of examples. Going sledding, on a roller coaster, skydiving. Those are all examples that we talked about in which you're converting potential into kinetic. Right? Anytime something falls from a fixed location, it's converting potential to kinetic. Now, here's what's key here. The energy is going to remain unchanged in a system. So what do we mean by that? Well, we've talked about many laws of conservation. Here's one more. We've talked about the law of conservation of mass, which says mass cannot be created nor destroyed, only changed. The same thing applies to energy. Energy can only be created or destroyed. Or excuse me, I said that completely wrong. Energy cannot be created nor destroyed. It only can be changed into different forms of energy, which means the following. The amount of energy that we had at the beginning of the universe is the same amount that is currently in the universe. It's just been converted into different forms. So the law of conservation of energy states that energy cannot be created or destroyed, only changed. So how do we study this phenomenon? Well, we talked about potential and kinetic are equal, which means that the potential energy of an object plus the kinetic energy of the object must be the same when an object falls. So what does this look like from an equation standpoint? Well, we have kinetic energy plus potential energy of our beginning object is equal to the potential energy plus kinetic energy of our ending object. So we have beginning and end, or what I will typically call initial and final. We will abbreviate with small i's for initial. We abbreviate with small f's for final. So if you take an equation like this, KE plus PE beginning is equal to KE plus PE final or ending. We know the equation for kinetic energy is 1/2 mv squared. So it's going to be 1/2 vi squared, our initial velocity, plus the equation for PE is mgh, nothing initial there, equals our kinetic energy, which is 1/2 mvf squared, vf being our final velocity, plus mgh. And it's going to be really hf as our final velocity, or excuse me, hf is our final height, and it should be hi is our initial height here. So just something to keep in mind. 1/2 mvi squared. I stand for initial or beginning. The f stand for ending or final. So if we take an example here, let's look at an example where we're going to have to try and figure out the conservation of mass. Or conservation of energy, not mass, energy. So here's our example. At a construction site, a 1.5 kilogram brick is dropped from rest and hits the ground at a speed of 26 meters per second. Assuming air resistance can be ignored. Guys, air resistance can be ignored every single time we do these problems. Unless you're going to be in the third year of your college physics class, we can always ignore air resistance. So, assuming we can ignore air resistance, calculate the potential energy of the brick before it was dropped. So, let's go ahead and do this. We are going to, let's isolate what we have. A 1.5 kilogram brick, what is that going to be? That's the mass of the brick, is 1.5. Is dropped, here's key word, it's not a number, it's a word. Is dropped from rest. So what is that? That's our velocity. Is that our final velocity or initial velocity? That's our initial velocity. VI is 0, dropped from rest, and hits the ground at a speed of 26 meters per second. What is 26 meters per second? Our final velocity is 26. Assuming air resistance can be ignored, calculate the potential energy of the brick before it was dropped. So let's go through here with our equation. We have PE plus KE, and this is beginning, right? This is our beginning, or our initial, is equal to PE plus KE final. Well, let's go ahead. What's our equation for PE? PE is mgh plus Ke is 1/2 mvi squared is equal to PE, which is mgh plus kinetic energy final, which is 1/2 mvf squared. So let's go ahead and let's plug this. Let's go ahead and plug in what we have and what we're trying to solve for. First, it says calculate the gravitational potential energy of the brick before it was dropped. So we are trying to solve for this. So we are trying to solve for this entire thing. So we are just going to leave that as PE, our PE initial, right? Plus 1/2 mvi squared. Let's go ahead. 1/2 times our initial mass, which is 1.50, right? Times our initial velocity. What's our initial velocity? 0 squared is equal to our final potential energy. Well, final, the mass of the brick is 1.50 times gravity, 9.8, times the height. What's the height of the brick once it hits the ground? The height of the brick when it hits the ground is going to be 0. Right. Plus 1/2 mv squared, 1/2 times the mass of the brick, which is 1.50, times the final velocity of the brick, which is 26. Now we are left with doing some math. PE initial is down below here. PE initial plus, what's 1/2 times 1.5 times 0? It's going to be plus 0 is equal to, what's 1.5 times 9.8 times 0? 0 plus 1/2 times 1.5 times 26. 1/2 times 1.5 times 26. And when you multiply that together, you're going to get 19.5. We ignore our zeros here, and PE initial is equal to 19.5. And what's our unit for energy always? Joules. Now, this is a complex problem, guys. I understand these are very complex problems. We're going to take some time working on these in class. It's going to take some time working on these questions in class. There's a lot of stuff to pull out. There's a lot of stuff to decipher. So I know you're capable of doing it. We just need to practice a little bit with these examples. So if you have questions on this quiz, the 15.2 quiz, let me know and we may go over it in class a little bit. So, this is the end of section 15.2. This is Mr. Clement, and I'm signing off.